So today I'll be talking about some of the work that I do as a PhD student. My name's Alex, by the way, and I'll start off by telling you a bit about myself, where I work, and what I do, and then I'll go straight into all the background, exciting science that that brought us here. So first off, a bit about me. So I'm a PhD student in my final year of study, doing astronomy and astrophysics. The main part of that is learning how to do research from the first level. And I've now been studying at university for almost 10 years. So where do I work? So I work up at Mount Stromlo, which is just on the outskirts of Canberra. There's this nice historic observatory that sadly doesn't function anymore. But my main work is studying the formation of gas giant planets such as Jupiter, which I'll get to later on. And we're trying to observe solar systems similar to our own that are still in the process of forming. So yeah, so that's enough about specifically me. So we'll get straight onto it, onto talking about all these amazing planets. So we'll start off with the first planets that were discovered, the ones in our own solar system. So we have 8 planets in our solar system. It was 9 for a brief period before Pluto was demoted. I won't be talking much about Pluto, so sorry if there are any Pluto fans. But one of the reasons Pluto was demoted is that the other 8 planets fit into this nice pattern, these nice 2 groups of planets. So we have 4 terrestrial or rocky planets in our inner solar system. So that's Mercury, Venus, Earth, and Mars. And what defines a rocky planet is that they have a solid surface. You can actually stand on these planets. Yeah, if you had a spacesuit for the other planets at least. And all of these planets are pretty close to the sun. So they're all in the inner solar system. And the other main type of planet, the other group we have are the gas giants. So, so this image is all to scale. You can see the giant planets are much larger than the terrestrial planets. So we have Jupiter, which is about 1,000 times the size of the Earth, 300 times the mass. And Saturn, which is a bit smaller than Jupiter, and then Uranus and Neptune, which are, again, still a bit smaller. And what the defining characteristic of these planets is that they have no solid surface. So if you tried to stand on one of these planets, you would just fall through the atmosphere, and you would just never stop falling, really. But also with these planets is that they're all far away from the sun, at least compared to Earth. And the reason for that is that it needs to be cold, because otherwise, as these planets are forming, they can't actually grab all this gas. It just boils away, essentially, and that's why there are no gas giants near Earth. At least that was the prevailing theory of planet formation. So these are all pictures from space probes that were taken relatively recently. But we've actually known about all these planets for quite a long time. So how do we actually find these planets? We have this sky, we have the mass of all these stars in our galaxy, as you can see in the photo below. And so, finding a planet amongst all these stars can be a bit of a challenge, but it's been done since ancient times. So before the age of TV, movies, internet, people had a lot of patience. So that was one of the main ways of finding a planet. Another is luck. So you need a lot of luck, and also you need to know where to look. So if you look in the right place, hopefully you can see a planet. So yeah, as I was saying, back in ancient times, people would go outside and look at the night sky in their spare time. So this is a simulated image of something you can actually see in the sky. So at the top is the constellation of Scorpius, amongst all these stars. But 3 of the objects in this image are not actually stars. They're planets. So if you were to come back here and to the exact same time, just a week later, you would notice that while the constellation of Scorpius has stayed exactly where it is, some of those objects have actually moved. And then if you go another week, one of them has disappeared. Then another 2 weeks, and another 2 weeks, and they're continuing to move across the sky. So if you go back to the original, I can reveal those dots you saw were actually the planets Jupiter, Venus, and Saturn. And what people noticed back in ancient times was that these were wandering across the sky. So the Greek word for wanderer is planetes, and that's where we get our word planet. And so that image I showed of all the stars before actually did have a planet in the top right there, which was the planet Mars. You notice it's quite bright and it's slightly stretched out, and that's actually a result of it moving across the sky as I took the photo. So we had so those 4 planets I showed plus Mercury have all been observed for thousands of years. So every ancient civilization has seen these planets. So we knew about those 5, and then eventually we realized that Earth was also a planet. So there were 6 planets that were actually known since ancient times, even though it wasn't until we pointed telescopes at them that we actually understood just how remarkable they were and what they actually were. But there were 2 planets in our solar system that couldn't be seen without a telescope. So I'll briefly talk about how those were discovered. So the first one was Uranus. So this was the first planet discovered in the modern era. So that was discovered by William Herschel, 1781. And the first thing he noticed was that this wasn't a star. So the key thing about planets is that unlike stars, they appear as disks rather than just points of light. So I've labeled that image there, so you can see there's a star there, and the one in the center is definitely not a star. So he thought that was a bit curious at the time, and then when he did subsequent observations, it moved against the background of stars. So this was another wanderer that he'd discovered, and yeah, so like I said, that was the first planet that could said to have been discovered at all, because we actually know when it was discovered. So after he discovered Uranus, it was possible to predict where it was going to be. So Uranus takes 84 years to orbit the sun. So I've got here a little simulation of what they thought was going to happen. It was going to be in this very simple, almost circular orbit around the sun. But then when it actually came to observing Uranus in the decades that followed, they found that its position was a bit off. It wasn't matching what they'd predicted. So I've got here a simulation of so the bluey green thing is where it actually was, and so you can see it goes a bit in front or a bit behind where the prediction said it was. And so the reason they put this down to was another planet's gravity that was pulling on Uranus, and thus it was so it was a planet that hadn't been discovered yet that was making their predictions a bit off. And so it's possible to use all they knew about gravity at the time to calculate where this mystery planet should be. And so that again comes back to looking in the right place. So they knew where this planet would be, and so they pointed all their telescopes, and so by the year 1846, they discovered an 8th planet, Neptune. So what we learned from this was that we don't actually need to see a planet to know it's there. We can actually feel its gravitational effect, or at least observe its gravitational effect on other objects before we can point our telescopes there. So from here on, we had 8 planets in our solar system, and to date, that's all the planets that have been discovered so far in our solar system. But this wasn't the end of the story. We then thought about our solar system, that our sun is actually only one star among 100 billion. So if you think about our galaxy, it's got 100 billion stars, and each one of them might have a system of planets. So that sort of intrigued us for a long time, and ever since we basically knew everything about the solar system, it's intrigued science fiction writers over the course of the years. So planets around other stars, we call them exoplanets. And so here I have 4 example planets from science fiction movies. But the interesting thing is all of these movies were released around the mid to late 20th century before we had actually discovered any planets around other stars in real life. So the big question is, how do we actually discover these planets around other stars? If those stars are just these small points of light, a planet's not going to be very significant. So there are several methods we would use to discover these planets. First one is simple, it's the transit method. So I've got here a video of the transit of Venus from 2012. And this is where we simply, so again, if you have any questions, I should say, just ask them in the comments below the video. So we have the first one is the transit method, where we simply look at a star and we wait for a planet to pass in front of it. And when that happens, the star becomes dim. So it actually blocks out some of the light. It's a tiny amount. So the graph on the right shows the brightness dropping by less than 1 in 1,000. But that's enough to detect with our modern technology. And we have actually discovered many exoplanets through this method, even though it seems like a bit unlikely that the planet would happen to block the light in the direction we're looking at. So, the second method is called radial velocity, and this is where we, similar to the discovery of Neptune, we look at the gravitational effect of the planet. So it's orbiting the star, but it's also pulling on the star. So as that happens, the star moves back and forth, and we can detect the change in the frequency of light as it moves back and forth. So, as the sun moves towards us, the light becomes a bit bluer, and as it moves away, it becomes redder. And from that movement, we can actually determine all sorts of things about the planet, such as its mass and its orbital period. So this was actually the first method that worked, and this is how we discovered our first exoplanets. So again, if you have any questions, just type them into the comments below the video. So I'll go straight into the first exoplanets that we've discovered. The first one that we're excited about, at least, which was 51 Pegasi b. So this was discovered around a sun-like star in the mid-90s, which was quite a big milestone. So this was it was the first star that was similar to our sun and also hosted a planet system. But it soon transpired that this planet was actually nothing like we'd seen in our own solar system. So it's about half the size of Jupiter. So that's not so bizarre. But its orbital period, as determined from the radial velocity measurements, was only 4 days. So that's quite different. So Earth takes a full year to get around the sun, whereas Mercury, the closest planet, takes 3 months. So we've got nothing like that in our solar system. So this was part of a new class of planet known as a hot Jupiter. So it's a planet about the size of Jupiter, but it's so close to the star that the atmospheric temperature at the top is about 1,000 degrees. So so this actually started challenging our very perceptions of gas giants and their formation. We first believed that they have to be much further out, otherwise the atmosphere would just boil off and run away, and they'd end up like something like Mercury. But then this turned out to be only the beginning of a lot of the strange worlds that we'd discovered. So through radial velocity and transit, we actually discovered thousands of planets. So I'll go through a few examples here. So, so the one on the left is a pulsar planet. So it's actually orbiting the dead core of a star. So these were some of the first planets discovered. So even before we discovered 51 Pegasi, we were already finding planets around pulsars. So this is after the star has died. It might have destroyed all life on these planets if there was any to begin with, but the planet has survived and it's still orbiting the dead shell of the star. And so the one on the right, as I said before, it actually is having its atmosphere boiled off. So basically neither of these planets could support life, but we have found some that could. So here I have, so it's a very small planetary system. It's quite close by, around 20 light years, which would still take thousands of years to reach in a spaceship. So I should also say these are all artist impressions. We haven't actually photographed these planetary systems. We've just detected their gravitational influence. So the planet in the foreground of this picture, we think is habitable, but another issue with this planet is that it's what's known as tidally locked. So it orbits the sun very quickly, like 51 Pegasi, but it's keeping one face constantly to the sun. So you can imagine that's a world where the sun never sets. It just stays in the same position in the sky, and on one side of the planet, the sun just never shows up. So the issue with that is that is basically life would be way too cold on one side of the planet and way too hot on the other. So it'd be difficult for life actually to survive. The reason we say this planet is habitable is that it's in what's known as the habitable zone, which is just close enough it's basically not too close and not too far from the sun, so that liquid water can theoretically exist on its surface. But with this planet, basically the only place where liquid water could exist is on the terminator, so the point between day and night, where the temperature will be just right. So yeah, if there is life on that planet, that is where we'd find it. But again, it's a bit of a long shot. So some of the other strange systems that we'd seen are actually orbiting multiple stars. So our sun is a single star, so it doesn't actually have any stellar companions. It's orbited by all these planets, but there are no stars nearby that are also orbiting the sun. Whereas the one on the left, Kepler-16, is actually orbiting two suns. So you would see a double sunset and a double sunrise, similar to the planet Tatooine in Star Wars. And the one on the right is actually in a triple system. So you can see the last light of one of the stars just setting behind those mountains in the artist impression. And then there are two smaller stars just above it. So these are all interesting systems, but so far we haven't actually seen anything familiar. So there's nothing that looks like this. So that image I showed before of these nice two groups of planets, the rocky planets close to the star, gas giants further away. So far we haven't seen any other systems that look like that. One of the issues for that is observational bias. So as I said, the radial velocity, you actually have to see the star moving back and forth, which only happens once every orbital period. Whereas the planet Jupiter in our solar system takes 12 years to orbit the sun, and we would have to see it orbiting a couple of times, which means it would actually take decades to see this via the radial velocity method. So there is another method which we can use to detect planets similar to the ones in our solar system. It's the simplest method, but it's also the most difficult, which is called direct imaging. So we have to ask the question, can we actually see an exoplanet? So one of the issues I touched on before was that stars are very bright and planets are very faint next to them. So the analogy usually given is trying to see a firefly next to a spotlight. You can't actually take a picture of that, so I've pasted in the picture of the firefly there. Do you have a feeling for that? But the answer to that question, can we actually see an exoplanet, is broadly yes, but with difficulty. So yeah, so like I said, the star is much brighter than the planet, but if we look for young planets, so planets that are still in the process of formation, we can search for them in infrared. So the planets, as they're forming, they're still quite hot, which means that if we look at them in the infrared wavelengths rather than what we can see with our own eyes, the planet should actually be glowing. It's not just reflecting starlight; it actually is glowing. So a planet like Jupiter would definitely put out the signature. So I've got an example of the infrared technique with a cup of coffee there. So the coffee itself is very hot, but if you look at that with your own eyes, you can't tell. It looks dark. You'd have to taste it or touch it to see if it's hot. But the image on the right shows that the coffee is actually glowing because now we're looking at it in the infrared. And so we have actually been able to directly image some exoplanets with this method. So this is one of the most exciting, which is the HR8799 system. So I've got a video here which you might be able to see. I'm not sure for the quality of it, but that's taken over a 7-year period of observations with the Keck telescope, and you can see 4 planets in there that are obviously orbiting the central star, which has been blocked out to make it easier to see the planets. And we have also seen planets in the process of formation. So planets form in these nice protoplanetary disks, so a bunch of gas orbiting the star. And so you can see there's a bright dot just to the lower right of the center. Again, the star has been blocked out in this image. So this is the PDS-70 system, which has only recently been discovered. And that was our first image of a planet actually in the process of formation. And you might be able to see, those with good eyes, might be able to see the bright dot is actually carving a gap in this disk. So there's a dark patch just in front and behind it. So that's where we are at the moment with our discoveries of exoplanets. The NASA database now has over 4,000 exoplanets. Most of them are giant planets. Quite a lot of them are hot Jupiters, and a small part of them are in the habitable zone. But if we look out at all these stars, there are many more that are still out there, including the ones that I'm trying to find during my PhD. So that was my last slide. So in summary, we've observed the planets in our own solar system for a very long time. But in only the last 30 years, we've discovered over 4,000 new planets beyond our own solar system. But most of these are very different from our solar system. And in order to see something familiar, then we really need direct imaging, and we need to improve this method substantially so we can see something relatively close into the star, like we've got in our own solar system, but also not too close for it to be a hot Jupiter. So yeah, that's it. So I can start answering questions now. So the first question was so very broadly, what happens if you discover an exoplanet? So the first thing that would happen is, at least in my line of work, you would publish a paper on it. If it's an interesting exoplanet, like something that might be habitable or the first one discovered in the process of formation, then it would go in the news. A lot of people ask, do you get to name it? To which the answer is most certainly yes, but usually, as you saw in the other slides, that a lot of them have rather boring names, which are just a string of letters and numbers followed by another letter. And a lot of the time, the star is actually named after the survey you're doing, because a lot of the surveys are specifically done to look for planets. And if you find a planet, then the star is usually called the wide angle search for planets, followed by some numbers. Yeah, but a lot of planets get nicknames, but they don't have any official standing. So again, like because there are so many exoplanets, you probably wouldn't be famous for discovering just one. But yeah, it'd still be interesting to discover one. I haven't yet in my PhD, but we've learned a lot about what we can and can't discover. So I had a question on the 51 Pegasi planet, and I guess that relates to our radial velocity technique. So it's would the star have a larger gravitational pull than the planet? So so that's a good question. So Newton's third law says that it loosely says that every action has an equal and opposite reaction. So the answer actually is that both the star and the planet are pulling on each other, and the size of the force that they're exerting is actually the same, so it's equal. So the planet pulls on the star and the star pulls on the planet with the exact same amount of force. But Newton's second law, F equals ma, says that if the object's acceleration, so the actual motion of the object, is inversely proportional to the mass. So the planet has a much lower mass than the star. So even though they're both pulling with the same force, the planet's the one that's going to get the most motion out of that. So there's another question: is why are exoplanets called exoplanets? So it's mainly a contraction of extrasolar. So extrasolar means a star other than our sun, and also exo can mean outside. So it's planets outside our solar system. So there's another one: is a hot Jupiter the same as a brown dwarf? Yeah, so the answer to that is no. So a hot Jupiter, like I said, is a planet similar to Jupiter, around the same mass and size, that's very close to the star. So it's actually hot because of the star's radiation beating down on it. Whereas a brown dwarf is actually sort of a failed star. So it's a star that so it was bigger than Jupiter, but it's not big enough to actually switch on and burn all its hydrogen. So there's a sort of division between brown dwarfs and planets. We're not entirely sure where that division is. So we might discover something through direct imaging that's 13 times the mass of Jupiter. And we'd say, is that a very big planet or a very small brown dwarf? And the answer is we don't really know. 13 Jupiter masses is considered the cutoff. So anything more than that is a brown dwarf, and anything less than that is a giant planet. But again, it's only a hot Jupiter if it's close to its star. So there's another question about planet naming, which I sort of covered on how exoplanets are named. So they're all named after the star followed by a letter, whereas the planets in our own solar system, apart from Earth, are named after Roman gods, and that all harkens back to when the planets were first observed by ancient civilizations. So the Greeks and Romans, among many others, saw all these things moving through the sky, and they believed that they're gods watching over them in the heavens, and then and it was sort of the Roman culture that then led into ours, and so that's why the planets have retained their Roman names. Yeah, so there's another question: can any planets pull their star around? So so I covered that with the radial velocity method. So the planets are all pulling their stars around, but the video I showed was a bit exaggerated, just to make it clearer. So what we're interested in with that question is the center of mass. So that's basically where all the gravitational forces are equal. It's what the planet and the star are both orbiting around. Whereas, but the problem with actually visualizing that is that the center of mass between the sun and the earth is actually inside the sun. So the sun is actually moving around, but you wouldn't actually notice it if you were to stare at it for a while. So they pull them around, but it's just not much. So there's another question: can there be a planet that's not orbiting a star? So yes, this is a good question. We think yes, that's possible. So all planets we think form orbiting a star from these protoplanetary disks. So they all begin orbiting a star, and then for whatever reason, a planet might be ejected. Maybe another planet got too close. The planets started orbiting each other, and then one of them got a bit too fast, and it was ejected from the solar system. So we call these planets usually rogue planets. But so far we haven't actually discovered any of them, but there are many surveys out there looking for them. Just looking through these questions. So there's another one. Am I using the techniques I mentioned in my research? So I'm not using transit or radial velocity to search for exoplanets. I'm actually using the last method, direct imaging, because I'm mainly interested in planet formation. So that's where we have to actually look at these stars, the protoplanetary disk, and we're trying to see something similar to Jupiter that's actually orbiting this star. And another follow-up question is: are we looking in a specific area or section of the Milky Way? So yes, we're looking at a place called the Taurus molecular cloud. So it's this big cloud of gas. It's about 400 light years away from Earth. Which actually makes it, like, believe it or not, it's one of the closest star-forming regions to Earth at only 400 light years. And so because there are so many stars that are there that are still young, we think this is a good place where these young planets are actually also forming. So we've got this good sample of stars that we can look at, and like I said, sadly we haven't actually found any planets orbiting them, but we have gained insight about our own limits. I should say we have found some brown dwarfs, and so we can tell they're brown dwarfs and not planets mainly by how bright they are. So the brightness of an object, a planet or star, can tell you something about its mass. And so the things that we have discovered, we think are too massive to be planets. So they're well above this 13 Jupiter mass threshold, but below the 80 Jupiter mass threshold that makes them a star and not a brown dwarf. So there's another question: can you have a planet bigger than its star? So the short answer is no to that. So our sun is about 1,000 times the size of Jupiter, 1,000,000 times the size of Earth. And stars are also much more massive. That's how the planets manage to orbit them. So that's always the case. If a planet were bigger than the star, then it would be a star. That's just what we'd call it. But in terms of actual size, though, so in terms of mass, absolutely, the star is always going to be more massive. But if you have a planet orbiting a pulsar that I showed earlier, so the dead core of a star, which is only about the size of a city, then technically you would have a planet bigger than its star. It just wouldn't be more massive than the star, which is sort of tangentially related to the question. So there's another question: can a star orbit another star? And yep, that does happen. In fact, it's extremely common. So we think at least half the stars that we observe in our sky are actually multiple stars orbiting each other. And we can't actually see that with our own eyes. We have to use very strong telescopes to see most of them. But one of them is Alpha Centauri. So one of the pointers very close to the Southern Cross that we get a good view of here in Australia. That's actually a binary star. It might even be a triple star. But if you were to look at that through a telescope, it doesn't even have to be a very powerful telescope. You will actually see two stars there, which will look like a pair of headlights in a car. So I've got at least one more question there, but if you have any more questions, please post them in the comments. Otherwise, we'll start wrapping up soon. So we've got so just one last question is, can there be a star orbiting a planet? Which sort of goes back to, can a planet be bigger than its star? Yeah, so the broad answer to that is no. So a star is always going to be more massive than its planet. So technically the planet is orbiting the star, but also they're both orbiting the center of mass. So you could say all stars are orbiting their planets as well, but yeah, but you'd probably be yelled at because because that's just a bit annoying. All right, so does anyone have any more questions? I don't see any other questions. All right, so I guess we can wrap up if there's nothing else. Yeah, that was an old question. Okay, yep. So we do have another question: is, can a brown dwarf orbit a star after failing to become a star itself? So I'd say yes, absolutely. So the brown dwarfs that we detected in my own research, that's exactly what's happened to them. So they all formed together in this molecular cloud. One of the stars was more massive than the other. Maybe it stole some mass from the other one, and so that did actually become a star. And then its companion failed to become a star, but still continued to orbit this star. So are there any more questions? So there's an interesting question: is, can a planet become a star? So that's interesting. It depends on this definition of star, which is a bit hazy. So we consider a planet to be anything less than 13 times the mass of Jupiter. So in order to become a star, it would have to put on a lot of weight, is basically the answer. So then the question is, where does it get that extra mass? So the only way it can do that is, so this is something I looked into briefly as part of my work, is if a planet's orbiting a dying star that's become a red giant, maybe the outer layers are expanding a bit more, and the planet's gravitational influence can actually pull some of the gas from the star. So that'll increase the planet's mass much later on in its life. But my honest opinion is that I don't think the planet can actually grab enough mass in the short amount of time available. So I would say probably not. I don't think a planet can become a star once it's already a planet.